Doppler's effect. Doppler's effect was named after Christian Doppler, who first came up with the idea in 1842. He thought that sound waves would have a higher frequency if the source was moving towards the observer and a lower frequency if the source was moving away from the observer. Doppler's effect is a phenomenon observed whenever the source of the wave is moving with respect to an observer. Doppler's effect can be described as the effect produced by a moving source of the wave in which there is an apparent upward shift in frequency for the observer and the source are approaching, and the downward shift in frequency when the observer and their source are receding from each other. So for sound, when the observer is moving towards a source, the formula is going to be given by F equals Fs V plus V naught over V, where V is the speed of sound, V naught is the speed of the observer. So the observer in the front of the source moving towards it will hear a higher frequency, as an observer moving away from the source will hear a lower frequency. Now, in a situation when the source is moving towards the observer, the sound source is radiating sounds at a constant frequency. However, now that the sound source is moving to the right, wavefronts are produced with the same frequency as before. So the wavefronts will collect at the front and then move back at the back. So in this case, the frequency shift will be given by F equals F of the source, V over V minus V of the source. Now there are two types of Doppler's effect, symmetrical and asymmetrical. Symmetrical is where Doppler's effect is the same when the source of light moves towards or away from a stationary observer, or the observer moves with the same velocity towards or away from the stationary source. Asymmetrical is the apparent change in frequency when the source of sounds moves away or towards the stationary observer, or as it occurs when the observer moves with the same velocity towards or away from the stationary source. So here's a picture of a sound wave generated by an airplane. This picture shows the shock wave generated by a twin-engine high-altitude supersonic trainer. And this picture shows the sonic boom created by the team car as it broke the land speed record. So look at it very, very carefully. Here's what it looks like. Now, Doppler's effect for light. Since light is an electromagnetic wave, Doppler's effect will hold for light as well. The Doppler shift formula, now we have to use Einstein's relativity formula, will be given by F0, which is almost equals to Fs 1 plus. This should be a plus V relative over C, where F0 is the frequency of the observer, Fs is the frequency of the source, and V relative is the relative velocity of the observer and the source. So if the light is coming towards us, Doppler's effect will say that the light will turn from red to blue. Whereas if the source is going away from us, the source was going away from us, then it will shift towards the red side. Applications of Doppler's effect. Doppler's effect in light has been used to know about other galaxies in the universe. It has been found that the wavelength of the spectral lines from the galaxy shows the shift towards red. We know that when it shifts towards red, it is moving away from us. Doppler's effect has led to the confirmation of hypothesis that the universe is expanding. Doppler's effect is made use in the speeds of the vehicles, knowing the speeds of the vehicles by traffic police, and it is also used in radar to detect enemy planes.